All right, so the first thing that when we deal with our right triangles, we're going to go through a couple different steps. The first one, we're going to talk about how similar triangles work. We're going to go into special rights. We're going to go into trig ratios. So it's going to progress all through right triangles. The difference is each section is very different from the rest. So it's going to feel like little chunks throughout this chapter. The first one I will tell you is nothing like the rest of the chapter. All right, so that's why I kind of want to do it a little bit separate. And it is called altitude on hypotenuse, and there's formulas that are going to go with this. And we're going to kind of take a look at a couple different ways to memorize it. The first one for at least the honors classes, when you look at what's called altitude on hypotenuse, we're going to draw our initial right triangle. And I am going to put the right angle up here at the top. And as we go through this and we practice, you're going to see I'm going to turn this right triangle around in a lot of different ways so that we get different looks at it. And then what we're going to do is we're going to take an altitude and we're going to draw it to the hypotenuse. Now, the trick here is understanding the vocabulary that I just said. An altitude, remember, goes from a vertex of a triangle to the opposite side and creates a perpendicular segment. And just in the last chapter, we did incorporate altitude with one of our proofs. So again, from the vertex to the opposite side. Now this one is specifically on the hypotenuse. So I don't really care about anything coming from C or from A. I specifically want it to drop to the hypotenuse. When that happens, how many triangles do you now see? 3. So we had our largest one that we started our drawing with, and that looked like this. And we had our right angle here, and it was simply A, B, C. And then we have this guy off to the left side, which is A, D, B. And then we have this guy off to the right side, which is C, D, B. Now, the trick is recognizing some of the things that are happening here. Obviously, all 3 of them have right angles. So no matter how you look at it, we know that these are all right triangles. The next thing that you want to take a look at is from the original picture, when we split up the triangles to look at all 3 of them separately, this guy right here, this angle A, that's over here. And the entire angle is sitting over here. This guy's considered reflexive. It's as if I picked this one up right off of this large one, set it off to the side. So angle A is reflexive, which means what other angle has to be reflexive? Angle C. So when we look over here, angle C has to be the same. Now, I want you to consider this, and a lot of times when it's difficult to kind of visualize just ambiguous measures, like we don't really care what they are, just numbers, sometimes if you put an actual number into your picture, it makes it a little bit more concrete. So if I just happen to make this a 30-degree angle, just again for example's sake, doesn't that mean this angle here has to be 60 degrees? So that 90 plus 30 plus 60 is 180-degree total triangle, which means this guy is 60 degrees. If I fill in the measures everywhere else, what's the measure up here? Has to be 30. There is no other way around it. It's got to add up to 180 degrees. And what's the measure up here? 60. So even if I didn't use the numbers to help me figure out what's really happening here, when I look back even at now the original picture, what do you notice about all 3 triangles? All the angle measures are the same. Are they all the same size? Okay, so they're not all the same size, but all the angle measures are the same. So what did we just figure out about what's the relationship of all 3 triangles? They're similar. So what we just figured out is bi-angle angle So by angle, angle, all of them are similar. Now, I didn't need to put the numbers in. Right away, what you need to pay very close attention to is that just by the reflexive angles, that was enough. Angle, angle, we had our right angles were congruent, and we had the reflexive angles that were congruent. So all three of these are similar by angle, angle. Now, what that means is if all the triangles are similar, we actually have proportionality statements that can happen. So because they're similar, we can write out proportionality statements. Now, notice this is just like the last chapter. So everything we just got done talking about is still applying into this next chapter. So what we're going to do is we're going to take a look at these three triangles. I'm going to redraw them over here so that we have a brand new clean slate to work with. And if our original picture again looked like this, A, B, C, we drop our altitude to D, and I wanted to look at what the proportionality statement is. What I'm going to do is I'm going to match up my pairs of triangles so that we're not working with extended proportions. Okay? What we're going to do is I'm going to number. The first one was the biggest one we drew, right? And then we're going to take a look at our second and our third one, just to kind of give ourselves a little bit of a pattern. So if we're talking about triangle ABC being similar to triangle, now again, I want to kind of put this in order. A we know is reflexive, so I'm going to start with A. We know that the right angles have to match in the same position, so I'm going to put D here, which means the only other letter left is B. So I'm still matching up each of the corresponding congruent angles so that my statement, my similarity statement, is correct. So this was essentially matching up triangles 1 and 2. Then what I'm going to do is I'm going to create another column so that I have a proportionality statement. And let's start again with, just to keep things organized, the big triangle. So A, B, C. So that was triangle 1 again. And now let's compare it to triangle 3. So watch how I write triangle 3 so that I make sure my letters are matched up. We already know that C is the reflexive angle. When I look at where I put C here, it's the last letter. So I'm actually going to make sure C is the last letter of this name so that I don't make any mistakes. They have to correspond. They have to be in the same spot. I know B is the right angle, so I'm going to make sure D is in the same spot, which now means the angle in triangle 3, as you see here, triangle 3, that doesn't have a reference yet, reflexive, right, here's this guy up here. That's actually the one that leads off. So I kind of try to make sure that I think, what do I already know is congruent, and then I match the letters up accordingly. The last comparison is actually the two little ones. And what happens is because they're both similar to triangle 1, kind of like the transitive property, they're going to be similar to each other. There is no way around that. So I already have them matched up in order with this. So the way I've written them here is the way they should be matched up. So I'm going to start with triangle ADB, and that is similar to triangle BDC. Everything I did here with my similarity statement is simply based off of my reflexive angles, my right angles, and again, very quickly going back to this idea that we know they're all similar by angle, angle. So I'm using the idea that I've proven them similar by angle, angle to create these similarity statements. I'm not even going to look at my picture anymore. These letters are enough to write my proportionality statements. So in this first one, AB automatically corresponds with AD. First two, first two. The second two, BC, corresponds with DB. And then AC, first last, corresponds with AB, first last. I'm going to do the same thing for the other pairs. Over here, AB, first two, corresponds with BD, first two. BC corresponds with DC, and AC corresponds with BC, first last. And I'm going to do it one last time over here. AD, BD, DB, DC, AB, BC. Doesn't this feel like we're reviewing the last chapter as we're going through this? And that's truly all that we're doing. So what ends up happening is because of the way these triangles are drawn, the way this is created, what we end up with, and I'm hoping that you already see it. You see that guy on top? Way over here, do you see it's on the bottom? If I was to create a proportion where I kind of got rid of that, what we end up looking at is something that looks like AB over AD, AC over AB. We know that we can take any two and actually create it to cross multiply, solve, all that good stuff. This guy right here, isn't he going to cross multiply and be something squared? What do we know from the last chapter that when we cross multiplied we got something squared, and to solve we took the square root? What was that called? The steps were multiply and take the square root. Does anybody remember? Yeah, the geometric mean. So what we just found out is AB is the geometric mean of AD and AC. And all I'm doing is looking at how the cross multiplication works. So if that's the theory, we're looking for this cross multiplication, I want to know, what do I have over here? Do you see that happening in this second set? BC. Do you see how BCs are across from each other? So again, I'm not going to worry so much about this one because I know I can take any pair and I can set them equal to each other to solve. Now I have BCs doing the same thing. And if I cross multiplied here, wouldn't it be BC squared equals these two things multiplied together? So what we just found out is BC is the geometric mean of DC and AC. In the last one, which one do we happen to have? Do we see that happening in the last one? This one always catches everybody because of the way it looks. We have to remember that it's the same segment. BD. I know that says DB and that one says BD. It's the same segment, it's just the way we named it. So again, if we got rid of that last one to solve a proportion, we now have AD over BD, DB over DC, and we have that is our geometric mean. So we can say BD is the geometric mean of AD and DC. So when we look at the original picture, what I want for you to do is I want you to talk about where you see each of those segments in the original picture. Where do you notice AB at in the original picture? Where do you notice BC at in the original picture? And where do you notice BD at in the original picture? If you look at AB, isn't that this side of the triangle? Now, watch closely. In the big triangle, isn't that considered the leg of that big triangle? But when you look at triangle 2, isn't it the hypotenuse? So kind of like the reflexive property, it's used in two different triangles at the exact same time. The length doesn't change. I'm going to say that again. Like the reflexive property, it's used in the big triangle, it's used in the small triangle. The length isn't adjusting. It's going to be the same length in both triangles. The difference is, do they correspond? Meaning, are they the same segment in both triangles? And when I say it again, it's the leg of the big one. It's the hypotenuse of the small one. Do they correspond? Remember, correspond means they have to be identical. So are they corresponding? Answer's no. If they corresponded, they would both be legs. They would both be hypotenae. It's the same segment. It's not corresponding. So when we talk about something being the geometric mean, same length, same segment, but they don't correspond. Same length, same segment, they don't correspond, which is why this cross multiplication occurs. If you look at BC, isn't BC going to be the same thing? It's the other leg of our original right triangle, but it's the hypotenuse of that small one. Same length, same segment, but it doesn't correspond, which is why we get this cross multiplication. If they corresponded, they'd go top to bottom. They don't correspond, which is why the cross multiplication happens. The last one is BD. Now this one's the only one that actually looks like our reflexive property from before, but it's not. It's the leg of our triangle 2. It's the other leg of triangle 3. And if I put all my tick marks in, you would end up seeing that back over here, BD is our geometric mean, but notice how on this side it's the longer, it's opposite the 60-degree angle, and over here, isn't it the shorter? It's opposite the 30-degree angle. So even though they're both legs, they don't correspond. And that's what happens when we talk about the geometric mean. Same segment, same length, they don't correspond, and that's why the cross multiplication occurs. What ends up happening is we can solve for sides of our right triangles and a bunch of right triangles, all three of them, given these proportions. I think we could both agree with just the 18 minutes that it took to talk through this. That's a lot of work to come up with these proportions every time. So what I did was I call them the formulas for our altitude on hypotenuse. Right here, if I multiplied AB, wouldn't it be AB squared? And then it would be equal to, now look where AD is. Isn't AD right off? It's at the vertex of that leg. And then AC, isn't it the whole side? So don't both segments come right off of A and they're along the hypotenuse? If you're over here with BC, isn't it the exact same thing? We said we're going to take BC and multiply it by BC. Notice what it is going to be equal to. DC, isn't that off of here? And AC, isn't it the longest segment? So isn't the pattern the same? Whether we're on this side, it's the short and the long. Whether it's on this side, it's the short and the long. It's the same pattern. When we look at BD, if we cross multiplied BD, it's BD squared. Notice, isn't it right off of D, short, short? But isn't everything that we set these equal to along this hypotenuse? So you have short, long, or short, short. So let's look at how to make this a little bit easier. I'm going to draw, and we're going to call these the altitude on hypotenuse formulas. Altitude on hypotenuse formulas. So here's my triangle again. This time I'm not going to label the vertices. I'm going to label the segments with variables. We're going to call this guy A, this guy B, and the whole thing C. Kind of makes sense, because isn't that the Pythagorean theorem? ABC. I'm going to name this guy H. So our altitude gets H, and we're going to name each of these little ones X and Y. Going back to our proportions and looking at where AB was in our original picture, what variable here corresponds with AB from our original picture? What variable down here matches with AB? A. When we cross multiplied up here, didn't we get AB squared? So I'm going to square A. When we were up here, we said AB squared was going to be equal to AD, which was short, and AC, which was long. So if I cross multiplied here and got short times long, what letters does that correspond with down here? X and short and, yep. Up here we said the same pattern happened on the other side of the triangle. We took BC and multiplied it by BC and got BC squared. What letter does that correspond with down here? B. So we're going to take B and we're going to square it. If the same pattern is supposed to occur off of this leg, what do we think it's going to be equal to? YC. Now the last one said BD, and we talked about that guy was right down the middle. We looked at what it should cross multiply with, and that's the AD and the DC, so it was short, short. So what letter does that correspond with down here? Perfect. H squared equals XY. Every time you do this, no matter what, doesn't matter how the triangles are configured, if it's more scalene than it is isosceles, as long as it's a right triangle and an altitude is dropped specifically to the hypotenuse, these will stay the same every time. I could change the letters to X, Y, Z, and V, LMNO, doesn't matter, as long as that's an altitude and this is a right triangle. Every one of these will happen, which means these will happen every time. So let's turn the triangle, look at one more way that we could write the formulas, and then I'll show you how we use the formulas, and then we'll be done. Everybody good? So I'm going to turn the triangle, and I'm going to rename the formulas. Here's my right triangle. Here's my altitude. And we're going to do G, H, F, E, D, and C. And obviously, you can tell I've repeated some of the letters. It doesn't matter what the letters are. It matters the positions. So, remembering that the geometric mean is the segment that's repeated in two triangles, but they don't correspond. Which three letters are considered our geometric means in this picture? Which three letters? Anybody? G, H, and C. Very good. Where do you see all of these coming off of? The original right angle right here. Aren't every one of those right off that original? The one end point comes off that. So that's a good hint as to that's the ones you're going to square. So we're going to take G, square it. We're going to take H, square it. And we're going to take C and square it. So again, whatever these are labeled, it doesn't matter as long as you see that they are right off that original right angle. G squared is supposed to be equal to short times long. So what two letters are we going to set it equal to? ED. So we're going to take whatever that length is, we're going to multiply it by D. What about H squared? What's that going to be equal to? FD. And what about c squared? EF, short. Each one of these is an equation. Each one of these stands for numbers. Once we know the numbers, we plug it in and solve. So the formula and understanding where it came from is the hard part. So here's an example, and then I will let you be for the night. That stinks. So what we're going to do is we're going to solve for x and y. Now, if we didn't have this formula, we wouldn't be able to use the Pythagorean theorem. Reason being is, even though in this original right triangle we have the hypotenuse, we don't know the other two sides, so we couldn't use a squared plus b squared equals c squared. If we only looked at this one, we couldn't use the Pythagorean theorem because, again, we only have one length. But now that we have this idea of similar triangles and the proportions, which through a very long explanation got us to our altitude on hypotenuse formulas, you could use this as your formula to follow, or you could fill in the rest of this triangle and write all three formulas. It doesn't matter to me, whatever's easier for you. I'm looking at x. If I want to solve this, what am I going to do to x in this picture? Square it. It's one of the legs. That's also a hypotenuse. It's our geometric mean. So when we go to work with this, we are going to take x and we're going to square it. It's kind of like h and g up here. What's it going to be equal to? 4 times 13, short times long, so if you have to, plug in that 13. And you end up solving, and you have x squared equals 52. And when you take the square root, x is equal to 2 radical 13. And it's awfully nice in these formulas, I find, because you'll see the factors right here. And in some cases, you already see one's a perfect square, the other one's not, and you can simplify. What am I going to do to solve for y? Yep, y squared equals 4 times 9, which is obvious that that's going to be 6. So do you see the geometric mean happening here? Multiply, take the square root, multiply, take the square root. Now, after 28 minutes, you understand that geometric mean isn't just a process. It's the segments in these similar triangles that get repeated, that act like reflexive, but they're not corresponding. And that's where our cross multiplying comes from, and then eventually solving with the square root.